friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 2, this is lecture 5 and we will continue with infiltration, that is infiltration part 2. And in this particular lecture, we will continue. We started with talking about mathematical models of infiltration estimation in the previous lecture. We will continue with that and we will talk about Horton model, Green-Ampt model, Phillips two-term model and Richards equation. Just to give a recap, we discussed in the previous lecture that infiltration models are classified as empirical, semi-empirical and physically based. In the previous lecture, we saw these two empirical models, that is Kostiakov and modified Kostiakov. Today, we will look into semi-empirical model, Horton's model and three physically based models, that is Green-Ampt model, Phillips model and Richards equation. Starting with the Horton model, it is one of the popular infiltration models developed by R.E. Horton in 1940. And it is based on the fact that infiltration begins at some rate f0 and exponential decreases until it reaches a constant rate fc, and this is the infiltration equation given by Horton, that is ft is fc plus f0 minus fc e to the power minus kt, where k is a decay constant. So, basically this model basically is based on what we have already seen, that infiltration curve. That is, it starts with at a higher rate f0, if you plot f versus t, and then it attains a constant value fc after a significant period of time. And it can be also expressed in terms of f, that is cumulative infiltration. Remember, we are saying infiltration rate, small f, and capital F is cumulative infiltration. So, this we must remember these two terms. So, capital F, it can be also expressed in terms of capital F or cumulative infiltration as a function of time. So, we have to integrate this equation 1 with condition f0 equal to at t equals to 0, and this is the equation we will get, which will give us the cumulative infiltration. The Horton model is simple in form and fits well to the experimental data. That is the advantages of Horton model. However, the principal weakness of the model is in the determination of reliable values of parameters f0, fc and k. If you remember, if you just look at the equation, we need these three, f0, fc and k, in order to be able to determine infiltration, either infiltration rate or cumulative infiltration. So, that is the main challenge, getting the reliable values of these parameters. So, in order to estimate these parameters, we take this is equation number 1, ft equals to fg plus f0 minus e to the power minus kt. So, if we take the logarithm of this equation, we will get this form, ln f minus fc equals to ln f0 minus ft minus kt. And when this equation 3 is plotted on a semi-log paper, we get a straight line, that is the form of y equals to mx plus c. So, here y is ln f minus fc, m of course mx, as you can see here it is mx and this part is c. So, here the slope is minus k and intercept is ln f0 minus fc. We can determine this. So, for a given infiltration data, fc is taken as the lowest value of f when it tends to become constant, and the value of f minus fc at t equal to 0 is f0 minus fc, that is the initial value to begin with. Let us take an example to be clear about this. For an orchard field, the time since start of the rainfall, accumulated infiltration and observed infiltration rate are given in the table. Develop the Horton model for the orchard. Also plot the observed and estimated infiltration rates. So, this is the experimental data given to us, that is time since the start of the rainfall, 3 minutes, starting from 3 minutes to 65 minutes, and we have accumulated infiltration value in millimeters, 0.34 to 3.08, and we have observed infiltration rate in millimeter per hour. Initially it is very high at 6.73, and then it becomes 2.32, that is the lowest value. Now, for determining the Horton model parameters, as we have already discussed, we need to fit the straight line relationship, that is, this is the relationship, and that means we need to plot ln f minus fc against time. So, that means we need to calculate this. So, these values were given: time from start of the rainfall or infiltration, experimentation, accumulated infiltration, and observed infiltration rate. And so, we take fc as the lowest value of infiltration rate in the experimental data. So, this is what we are taking, fc equals to 2.32, which is listed here. Fc is 2.32 throughout. So, now we know f, we know fc, so we can calculate the value of f minus fc, and then we can take the logarithm, and this is the value, and this is what we need to plot against time. So, when we plot ln f minus fc against time, this is the curve we get, and as we have already seen that intercept is ln f0 minus fc, and slope is minus k, that from this equation we have seen. And this is the equation fitted using Excel. One can fit using manually also. So, from the plot, intercept value we get is ln f0 minus fc, we get is 1.074, that is here, and so from here f0 minus fc is 2.93, or fg value is 5.25 millimeter per hour, because fc value we have taken is 2.32. Also from the plot we see k minus k is minus 0.0791, that means k equals to 0.0791. So, now we know f0, fc and k. So, that is why the Horton model for orchard is f equals to 2.32 plus 2.93 exponential minus kt. So, k value is 0.0791 t, and t is in minutes and f is in millimeter per hour. So, this is the Horton model we have fitted using the given data for the orchard. Now, obviously, we have been also asked to plot the values. So, this is the observed infiltration rate, and this is the estimated infiltration rate, which is calculated using the developed Horton equation just now we saw in the previous slide. So, these are the values against the measured values, and if we plot this, that is the plot of observed and estimated infiltration rate against time. So, if you see here, the observed is blue color and the orange color is estimated, and as you can see that from time t onwards, the data fits very well, but it does not do so well in the beginning. So, we can infer from this that the developed Horton model fits the observed data well, except for the initial period. As you can see that in the initial period it does not fit the observed data well, and that is how we can really. So, now we come to the next model, which is Green-Ampt model, which is a simple model developed by W.H. Green and G.Ampt in 1911, though it is a very old model, but it is a very popular model even today. And it is based on Darcy's law for infiltration into uniform soil with uniform initial moisture content due to pool of negligible depth of water. So, these are assumptions here, that is the soil is uniform, that is the soil column we are considering, that is a uniform, and it has a uniform initial moisture content, that is throughout the initial moisture content is uniform, and there is a negligible ponding depth on the surface. And water is assumed to infiltrate into the soil, which is quite obvious, and the infiltrated water defines a sharply wetting front separating the wetted and unwetted zone. So, as we saw in the infiltration process when we discussed, then obviously the infiltration will start, then there will be the soil will be wetted, because there will we saw that saturated transmission, transition transmission and wetting zone. So, this is what it is, and then lower boundary is wetting front. we also saw. So, that means if wetting front has gone up to a depth of L, so above wetting front there is a wetted soil, and below this wetting front there is unwetted soil or dry soil or having the initial moisture content. And so, that means, and this is what we are saying, that a ponding depth is H0, which is negligible. And this picture also shows the similar thing, that we have water ponded to a small depth on the soil surface, infiltrating water, that is H0 here H0 also, and the water has penetrated, the wetting front has gone up to L, that is wetting front has penetrated to a depth L in time t since infiltration began, and of course, this is the wetted zone, wetting front and unwetted soil. So, basically the pressure gradient you can see will be in this direction. The total head causing the flow or the downward movement of the wetting front will be because of these three components. One is H0, that is the ponding water depth, and L, that is the wetting front, that is the depth to which the wetting front has penetrated, and of course, psi, which is the metric section or soil suction head, which pulls water into the dry soil. That is a pulling force also there. So, there is a gravitational force because of and the head, and then of course, there is this pulling force. And this wetting front moves down into the dry soil because of this metric section, and soil texture of course affects the shape of the wetting front, and this concept was given by Chow in 1988. Now, if we look at the left side of it, then we said earlier that this control volume has uniform soil and uniform initial moisture. So, if we say that the initial moisture was theta I throughout the entire depth, then obviously when the wetting front moves down, there will be change in the moisture content, and because the constant head is maintained there, negligible. So, of course, the moisture will be, it is a uniform soil, the moisture will be uniformly there. So, we may say that change in the moisture content for the entire profile is delta theta, and here the porosity of the soil is eta and effective porosity of theta E, and there is a residual moisture content on the soil. So, there is a residual moisture content, there is a initial moisture content, this is the change in moisture content, this is the effective porosity, and this is the porosity of the soil. So, because of floating front, the moisture content of the soil is changing and it is increasing by magnitude delta theta throughout. That is what this entire control volume shows to us. Now, the GA model results from the application of Darcy's law to the wetted zone, and Darcy's law, you know, V equals to Ki, where K is the hydraulic conductivity and I is the hydraulic gradient, and of course, same thing is here. F is infiltration rate, K is a hydraulic conductivity of the wetted zone, and this I is the hydraulic gradient, that is the head causing the flow and the flow length. So, we already saw that there are three components here, H0, L and psi, and of course, the wetting front has moved up to a depth of L. So, distance from L is the distance from the ground surface to the wetting front, and psi is the capillary section or soil section at the wetting front, just now we saw in the previous picture. Now, we also said that this ponded depth of water is negligible. So, neglecting H0, this equation can be written in this form, F equals to K L psi by L. Now, if delta theta is the change in the moisture content in which we saw, and we also said that the porosity of the soil is eta, that means upper limit of the soil, this delta theta is eta, that means when soil is completely saturated, then it will be having the moisture content will be equal to porosity. Thus, cumulative infiltration we can say is delta theta times L, L is the depth and delta theta is the change in the moisture content, or we can write that L is equal to F by delta theta. And if we put this into equation number 2, this is what we get, F equals to K L plus psi by L, and now in place of L if we write F by delta theta and we manipulate, this is what the form we get, and this is nothing but the Green-Ampt model. Now, equation 3 we can this is the equation 3 we can also write in this form, F equals to K plus AK by F, where A is psi delta theta. Now, the advantage of this form is that if measured infiltration data are available, the values of 1 by F are computed and plotted against time, and if you plot that, this is nothing but also y equals to mx plus c, the form of y plus mx plus c, where the c intercept is k and m is ak, because 1 by f we are plotting. So, the slope is represents ak. So, by fitting the straight line through the data points, we can get the values of k and a from this plot. Let us take an example. Feed the Green-Ampt model, infiltration model to the data in example 1. Also plot the observed and estimated infiltration rates. So, this is the data we have seen already in example, where time, accumulated infiltration and observed infiltration rates were given. In this case, we have to plot f against 1 by f. So, that means f value is already given to us. What we need is calculating value of 1 by f. So, f is capital F is given. So, we have to find out 1 by capital F, and that is what is this we are showing in this column. And then this column, these two columns will be plotted against each other. So, this is f against 1 by f plot, and from here, as we saw, we fit a straight line which comes out to be here, and then we can find out the values of a and k. So, here from the plot, intercept k is 1.7674 and slope ak is 1.3363. So, from here k value is 1.7674 and a value is 0.76. So, the fitted Green-Ampt model for the orchard comes out to be in this form. And also we can then observed infiltration rate is there, we can use the fitted model to get the estimated infiltration values, and then we can plot the observed and estimated infiltration rate. As you can see here, here also blue color is observed infiltration rate, orange is estimated infiltration rate using the Green-Ampt model. And as you can see here that that even in this part, this model does better than the Horton model, because it is more physically based, more physical concepts are being used in this model. So, as evident, the developed GA model fits the observed data well, better than the Horton model, even for the initial period. So, that shows that Horton model is because it's a physically based, so it's slightly better than the semi empirical Horton's model as we saw earlier. So, now we come to the next model in the physically based category, which is Philip two-term model. And for uniform soil with uniform soil moisture content and excess water supply rate at the surface, Philip 1957 found a solution to the flow equation in the form of an infinite series. So, here if you look at the assumptions, the soil is uniform, the moisture content remains uniform, but there is excess water supply at the surface. In the case of Green-Ampt, we assume that there is a negligible ponding depth, but here there is a excess water supply. So, water is not a limiting factor, and under these conditions Philip found this infinite series, and because of the rapid convergence of the series, the first two terms of the series are considered sufficient and constitute the Philip two-term model. That is why it is called two terms are used, that is why Philip two-term model. And as per this model, F capital F, which is in cumulative infiltration, is S t to the power 0.5 plus A t, or infiltration rate F is 1 by 2 S t minus 0.5 plus A. So, first equation gives the cumulative infiltration, second one gives the infiltration rate. And here S, the parameter S is absorptivity, which is a function of initial and surface water contents of the soil, and soil water diffusivity, and A is parameter depending upon soil properties. So, these of course both are soil properties, both A and S. Now, coming to absorptivity, Philip described absorptivity as a measure of the capacity of the medium to absorb or dissolve liquid by capillarity. So, only if capillary forces are there, So, if we consider a soil medium, whatever liquid or water it could absorb or dissolve, that is absorptivity. And basically he showed that absorptivity can be determined from horizontal infiltration when water flow is mostly controlled by capillary absorption, and proposed the following relationship for absorptivity: F equals to F by underscore T. Now here remember it is a horizontal infiltration, because typically in the vertical infiltration case where we saw it in the description that while discussing the infiltration process, that the gravitational forces act predominantly. So, in the case of absorptivity definition, which Philip said that it is under capillarity only. So, that is why we have to have horizontal infiltration measurement, and then if when the flow is controlled by capillary absorption, then this relationship holds good, that is S equal to F by square root of D. For parameter A, Philip 1974 recommended a value of 0.6363 K as resulted in a realistic estimation of infiltration rate. However, he cautioned against the use of PTT model for large time. So, that means if you want to use a model for longer period of time, then Philip two-term model probably is not the a good one, but for short period it does well. Now, in the another term which comes is soil water diffusivity, which is defined by this equation d theta h k h dh by d theta, where kh is the hydraulic conductivity, is a function of pressure head, and absorptivity can be found if d theta and h theta are known. And if you have read in soil science, and if you have done the experiments, or if you have read about the pressure plate apparatus, then probably you will remember that basically this soil retention curve, this experimentation gives us the soil retention curve or H theta relationship, or H psi or H theta, whatever you call. So, psi theta or H theta relationship it gives, and once we have H theta relationship, then there are several models. One very popular model, Van Gunsten model. Using that Van Gunsten model, we can also develop K theta relationship. So, H theta relationship can be obtained from pressure plate experimentation, and based on that we can fit the data and get the K theta relationship. So, if you and of course, when we have H theta K theta, then we also can express K in terms of H. So, that is what is being used here. So, knowing that, we can find out the d theta, and if d theta and h theta are known, absorptivity can also be obtained for any given soil from the experiments. And parameter S in A can be obtained from empirical fitting if infiltration observations are available, similar to previous equations like Horton and Green-Ampt. And the observed values of F are plotted against the values of T minus 0.5, that is the equation we saw, and this is the equation, F equals to half S T minus 0.5 plus 1. So, if we plot F against this, then obviously we can, on an arithmetic paper, will get a straight line relationship, and then the intercept of this line is A and slope is S by 2. Now, we come to example 3 that fit the PTT infiltration model to the data in example 1. Also plot the observed and estimated infiltration rates. So, this data we already saw earlier, that is we have time since start of rainfall, that is T in minutes from 3 to 65. Observed infiltration rate values in millimeter per hour were given. We also had cumulative infiltration, but that is because that is not required in this PTT model. So, that is why that is not shown here. So, for fitting the PTT model, we need to plot F against T to the power minus 0.5. So, obviously, in this case F remains as it is, but we need to manipulate this, that is we need to find out T to the power minus 0.5, that is for each value of T we will calculate this. And then of course, we can plot F against T minus 0.5. and this is what we get. So, in this case, when we plot the straight line relationship, of course, we get y equals to 7.97 x to the plus 1.16. That is the equation. As I said that I have used Excel to fit this line and for giving this equation, but one can also use the least square method or any other software, or even manually using a calculator we can calculate and fit this equation. And we know that from the equation, because if you remember, the equation is of the form f equals to half s t minus 0.5 plus a. So, from here we know that the slope of the line is s by 2 and intercept is a, and the values are already given. So, intercept value is 1.16. So, value of a comes out to be 1.16. The slope s by 2 is 7.97 here, s by 2 is 7.97. So, s value comes out to be 15.94. So, that means we know the value of a and s, that is the two parameters of the Philip two-tone model. So, that is why we can put the values of s and a, and we can get the equation, that is f plus equal to 7.97 t to power minus 0.5 plus 1.16 is PTT model for the orchard data. And then of course, we can use this model to get the estimated infiltration values for different times, and then we can plot the observed infiltration rate and estimated infiltration rate, which is shown here. The figure shows the plot of observed and estimated infiltration rates against time by PTT model. As you can see here, that the blue line again shows the observed infiltration line, and orange color shows the estimated infiltration. But if you recall, if you see remember the previous equations, even the Horton model, right after 10 minutes beyond, there was almost a perfect match between the observed infiltration rate. And also in the case of Green-Ampt model, in the initial phases also the model was matching well. But here, as you can see that even in 10 to this period, this model either underestimates or overestimates. So, here it is overestimating, here in this part it is underestimating. So, this part is underestimating infiltration, this part it is overestimating the infiltration, even if we forget about the initial portion. So, that simply means that though it fits the data well, but it does not do as well as the previous two models. So, fit the data, observed data well, but it does not do as well as the Horton model or the Green-Ampt model. So, with this we come to the last model, that is Richards equation, which was given in 1931, and it is the most popular physically based infiltration model. It uses the one-dimensional continuity equation and Darcy's flow equation to derive the infiltration equation. So, this is one of the most prominent physically based infiltration model, and it uses the concept that soil hydraulic conductivity K increases with the moisture content theta, that is K. If you plot K against theta, then this is the kind of curve we will get for different soils, and hydraulic conductivity decreases with the soil suction psi, that is the metric potential head. As I already mentioned that we can use the pressure plate operators to get the S theta data, and then we use some models to fit K theta data. So, we can also get the K versus H and K versus theta values. So, by combining Darcy's law and continuity equation, we can write the Richards equation in terms of moisture content. This equation is given in terms of both moisture content as well as head, and this is in terms of moisture content. Del theta by del t is del by del z, d theta del theta by del z plus k theta, and d theta we have already seen, it is nothing but soil water diffusivity. We will discuss while discussing the PTT model, we discussed that d theta can be obtained if you have kh or k theta relationship, and which we said that this can be obtained using this pressure plate operators and by fitting the k theta model. So, by using this, so this way we have seen that infiltration can be measured in the field, and also it can be determined using the different kinds of models, be it empirical, semi-empirical or physically based models. With this, we come to end of this lecture. Thank you very much for listening to this lecture. Please give your feedback and also raise questions so that it can be answered in forum. Thank you very much.